Thank you very much. It's a great honor to be here, celebrate Manjul. I guess I should tell one story at least. I remember the days in which he was a graduate student, used to come to talk to me and to Andrew Wiles, giving us his amazing reports on his progress, especially on the use of pre-homogeneous vector spaces to count number fields. I'll actually return to that in a minute. And then at some point he comes and shows us now the theory of pre-homogeneous vector spaces over the complex numbers existed, and it was in good shape, but over the integers it's new, and he was developing all the tools. And then he found this composition law out of nowhere. I remember Wiles and I saying, who on earth ordered that? It's like there's a famous story about physicists saying, who ordered that? We didn't order that. None of us ordered that. And soon after that, I think Wiles turned to me or the other way around and said, guess we'd better make him a professor here soon before any other place tries to hire him. Which happened, I think, is the youngest professor, or maybe him and Charlie Fefferman ever made professors, I think, at Princeton. Anyway, something like that's true. And it's great to celebrate this occasion. The work I'll talk about here is joint. One half is joint with Bourgain and Gamburd, the second half, and the first half is joint with Untitled Ghosh. So let me explain what we're going to be doing here. We'll be working over the integers, but let me remind you, and this already came up in the first talk, where Dick Gross explained eventually one gets down to count. One sets up some very tricky or sophisticated counting problem, and I like to think of Manjul as the Herman Minkowski of our generation. That's the way I describe him. He has taken geometry of numbers to a completely new level with the sophistication of what we can count. But in the end, when you come to count at the end, there's always a problem that is highly non-trivial that has to be resolved, and it's something of this nature. You have an invariant, and you saw an example in the previous lecture, and I'll illustrate one of these in a minute. There may be more than one ring of invariant, and it may be that you need Windberg's theory, and it may be that you, in the pre-homogeneous vector space case, let me stick to that, where there's only one invariant, and it's preserved linear group action. So one of the themes I want in this thing is to replace a linear group by a nonlinear action, a morphism group, which, and to maybe explain that the whole theory can actually branch out quite dramatically. So we have a subgroup, everything's integers, the subgroup is a subgroup of GLNZ. It's defined by some orthogonal conditions, or maybe no conditions, just GLNZ, but it'll always be an arithmetic subgroup in the setting in which Manjul sets such a thing up. And then looking at the values, so I want to emphasize the form is of degree n in n variables. And you're looking at d of x equals k. I'm going to give an example in a minute. And so you expect to hit each k roughly a bounded number of times. That's not quite true, but that's the subtlety here. The group acting on these level sets, it preserves that, and they count orbits. The fact that they count finitely many orbits in this kind of setting is just reduction theory of Gauss, generalized by Borel and Harishchandra in this thing. So there will be finitely many orbits when the number of orbits with a given k is a very subtle invariant. The average value is something you can compute, because if you use this reduction theory, you land up in a big region, and you're counting integer points in the region, and the integer points are underneath d less than or equal to x. And the real difficulty there is if the region were dilates of a compact region, it would be very easy. It would just be Riemann summation, which counts the number of points. But there are what I call tentacles. So whenever he came into my office those days, I would say, how the tentacles? Because he had to handle them. And that's the technical part. And some people who worked before, as I'll mention in a second, actually weren't able to handle that. It was one of the things that was quite remarkable. So rather than go to the general case that was brilliantly solved by Argavai in his thesis in 4 or 5 papers in the end, let me go back to Davenport, which is counting cubic number fields, because I'm going to be interested in something very similar, although everything I say is got the same flavor. So the discriminant, if you want to count cubic fields, you can reduce it, after some thought, to counting binary cubic forms, irreducible binary cubic forms. The discriminant of a binary cubic, there are 4 variables, is a homogeneous form of degree 4 in 4 variables, just like I explained. And the action on the level sets, d of x equals k, is by GL2z. This is the same action that Dick threw away on the first sentence he uttered this morning. It's the action that's very important here. So you have these orbits, and you have binary cubic forms of discriminant k, and you want to understand hk, the class number. And what happens is if you reduce using GL2z, as Davenport does, he doesn't need Borel and Harish-Chandra here, he's just using Gauss's reduction, you get into a certain region with these tentacles, and he has to cut off the tentacles, and that's because the number of reducible forms, when you want to count cubic fields, you naturally would have an extra log countable points, and the number of fields eventually, or 3 parts of class groups of quadratic fields, is only a constant times k, and in fact that's what Davenport counts. He counts Heilbronn and Davenport. They count the number of fields of cubic fields of discriminant less than x asymptotically with some constant there, using this technique. And the key point is you had to remove reducible cubics, and those reducible cubics basically lie near these cusps. And that's to understand. One might ask, how many k's are there? So this is a Hasse type principle. For which values of k, which numbers are discriminants of cubic fields? We now know the numbers counted with multiplicity up to x, but which actual numbers are hit? So they made congruence obstruction. We always take that into account. And then we ask, do we hit everything we're supposed to hit? Well, you don't. And there's a prediction of how many you would hit. And that's because you can reconvert this problem into a problem of the 3-part of a class group, and then you can apply Cohen-Lenstra heuristics, which are not about the average, but about how often the 3-part is something, and that will give you that a positive proportion of numbers are supposed to be hit. And I'm going to be looking at this problem as a problem of homogeneous equations, or affine varieties, and trying to count the number of integer points and Hasse principles in a second. So Manjul's great achievement was to generalize or extend Davenport to quartic quantic fields and say that the use of pre-homogeneous vector spaces in this context is due to Yuki and Wright, though if you want to solve a quartic equation by intersection of 2 quadrics, it goes back to the Rubaiyat of Omar Khayyam, as is noted in their paper, by the way. Apparently they got this idea of using the pre-homogeneous vector spaces, which is so crucial, from Lustig. Yeah.
X1 and X3.
I resign. I was writing this down. Okay. I might not know what the discriminant is. I thought I copied it from Davenport, but probably miscopied it. Right. This is the well-known work, and I'm going to return to some other point of Manjul, but I now want to change gears and look at a nonlinear theory of this type. So I'm going to look at cubic affine surfaces. So that was like, I'm going to write a homogeneous form equals k. So the simplest thing you could think of is maybe a product of 3 numbers equals k. That's a torus. And tori we understand very well. In other words, how many ways can you write k as a product of 3 numbers? By definition, that's called D3 of k, and we know a lot about this. Every k is represented. There's no group that's relevant here because this is a split torus. So a split torus is a very simple thing. I won't look at it again. You took an anisotropic torus, so that means a norm of degree 3 of an order of a cubic number field, which is not split, and you ask about solving n of x equals k. You can solve that primarily because there's this famous theorem of de Richter that the group of norm 1 elements, so this came up actually in Dick's work also. You need to know at some point in all these kind of works what numbers are norms. The theory of the algebraic number theory answers that. In particular, the de Richter theorem answers that. They're infinitely many. They're very sparse. And the which k's are hit, well, that's something. If the class number is 1, you have a local to global principle, and otherwise the class number intervenes. So it's a subtle question of which numbers are hit, even for a torus. But I'm actually much more ambitious in this lecture. I want strong approximation. Strong approximation will mean that if I look at the solutions to this Diophantine equation and I reduce mod p, I really want to see all the solutions mod p. And a torus never obeys strong approximation. Never. And it's simply the fact that one the group of units is a finitely generated abelian group. So it's like the question of asking, is 2, or any quadratic Fibonacci number or something like this, but is 2, the multiplicative powers of 2 mod p, do they get all the multiplicative elements of mod p z star? Well, we don't even know there are infinitely many p's. Your brother knows that maybe not for 2, 3, and 5, but then otherwise it's true. It's called the Artin conjecture. But certainly there are many p's for which it's not on 2, and so you never have strong approximation for a torus. But you do have for a semi-simple group. And I'm going to be looking at nonlinear versions of this, which seem to be beautiful. And that's the whole point of this lecture. But before I do that, let me just explain how difficult these problems are, just in case you think such problems are trivial. I'm looking at a surface. I'm not looking at rational points. They're easy. Once you have points on a cubic surface, rational points, you can make new points by geometric constructions, just like you do on an elliptic curve. And Manin has a beautiful book called Cubic Forms, where he explains the structure of this operation. But if I start with a surface like sum of 3 cubes, which numbers are sum of 3 cubes? I allow negative, by the way. Negative. X can be negative. K is anything. Mankind knows nothing. Okay, there's a local congruence construction, which is easy to learn. If K is 4 or 5 mod 9, you will have no solutions. But otherwise, you could believe that XKZ, there's no local obstruction. I think many people might believe that XKZ is always not empty, and even infinite, and even might satisfy strong approximation. The trouble is you can't even do numerics on something like this, because the solutions are extremely sparse. And I'll return to this. So mankind knows absolutely nothing about this. There's no descent. And the point is that we don't know how to make new integer points from old integer points, and we just don't know where to start. There is one theorem, or one idea that has been successful here, and it's due to capitals, to use cubic reciprocity to show that the very strong form of strong approximation, well, I mean by that there is a number in, say, with k equals 2 over there. Castle's pointed out that mod 9, you can't get every congruence class that you should be able to get. And that comes from cubic reciprocity, and that's generalized by Heath Brown, to develop it for general K. Kolyop, Thelen, and Wittenberg reformulate this as a Brouwer-Manin type obstruction. It's the same global reciprocity being put in as an obstruction. And so it's always true that you will miss some congruence class. But if you work mod P for a large prime P, for all we know, there's no problem. You will hit everybody. And there's no Hasse failure. So basically this is the kind of thing I want to study, but we know nothing about it. So we're going to change here because we want to be in a position where we have a group action, but it will not be a linear group action. And these are these Markoff surfaces. So they're not homogeneous, but I'm looking at an affine variety, and I'll call this xk. So it's a sum of 3 squares minus the product square. There are variants on this, many variants on this, but I want to explain that the quadric, the flipping of signs, which was so important in the previous chapter, is the reason these can be studied at all. And this goes back to Markoff in the case k equals 0, as I'll explain. So the key point is that there's a descent on these xk's. I'm looking at the integers, but there's a descent algorithm, or a method of taking a solution and making it simpler. And that descent comes from the very simple observation, I think these are called Beata transformations, that if you fix x2 and x3 and you look at x1, the way that's set up is it's x1 times x2 times x3. There could be coefficients there, that's not a problem, but the cubic term, it's like a Weierstrass form. The cubic term has been brought out as a product of 3 numbers. So if I fix x2 and x3, then x1 satisfies a quadratic equation, I can flip the roots. And that's a transformation of the surface to itself, which is actually given over z. So R1, this Beata move, takes me from x2 and x3 are not changed, but I flip the root. And that's a quadratic expression. So the minute I start iterating these, I'm going to get a nonlinear action on affine 3 space. But the most important thing that allows us to start to study this is that these R's, they are invertible and have integer coefficients. So they take integers to integers. And the group gamma generated by these 3 involutions, these 3 Vieta involutions, coupled with the permutations of x1, x2, x3, and also switching 2 signs, which will also preserve that, to 2 coordinates, I could switch the signs of 2 of them exactly, will not change that expression. I'll call that group gamma. It's a finitely generated group of polynomial morphisms of affine 3 space. Okay, that's the mother of this. We sell everything for this guy, because it preserves xk, it preserves xkz, and I'll tell you that there are only finitely many gamma orbits, and they will be like the class numbers of what we had before, and we could try study them, and that's what we're going to try study. So the important thing, there's a descent procedure, so that if I want to understand whether that's got integer solutions, I have a very good chance of understanding that, because maybe this group is sufficiently rich to do a Gauss-type reduction theory and bring a guy from infinity to some compact set and then say, well, if there's nothing in the compact set, then I don't have any solutions. Maybe there's a fundamental domain even there for this nonlinear action. I want to emphasize that in the homogeneous world or abelian varieties, one uses linearity heavily. The composition of 2 linear maps is linear. This is very useful. But the composition of 2 nonlinear maps blows up in your face, and you all know that if you just want to study x goes to x squared plus c in the plane and understand that dynamics, this is extremely complicated. So we hope we're not going to face some complications, but we're going to face something of that nature. I want to also point out that these surfaces come up in many different contexts. And so this example that I'm going to study throughout this lecture is just the first of a slew of examples where you have an affine variety with certain geometric properties which have many integer points and don't violate conjectures of Voigt and things like that. So this variety, which I'm calling Markoff-like surfaces, because the one case is the one he studied, is actually the character variety of the representations of the fundamental group of the once punctured torus as a curve into SL2, into the group SL2C, say. So if you take it's a free group, the fundamental group of a once punctured torus is a free group, and you want to represent that as 2 by 2 matrices, so you can take A to any matrix and B to any matrix. But that's a representation variety. The character variety is where you now divide by simultaneous conjugation. So we all learn Jordan canonical form when 2 matrices are conjugate, but when are 2 matrices simultaneously conjugate? That's the question that's closely related to this. So the representation variety for the once punctured torus has a model, and that model is that cubic that I wrote down, where K is the trace of the commutator of A and B. So you have the generator A goes to a 2 by 2 matrix, B goes to a 2 by 2 matrix, and then the commutator AB goes to something which is fixed. That's the equation is that equals K is the trace of the commutator. You automatically get, by this, if you take this moduli or this parameter space definition of this character variety, then the mapping class group acts on this character variety quite naturally. And the group gamma, which I'm calling the Markoff group, is nothing but the mapping class group in that example. But this applies quite generally. And all these varieties have a definition. This is already in Fricker and Klein, by the way. All these varieties into SL2 have a definition over Z. So these character varieties are defined over Z, and the mapping class group, which is a beautifully large discrete group, acts non-linearly on this character variety, preserving taking integer points to integer points, and we can ask, are there finitely many orbits? So it's a nonlinear theory, very similar to the usual familiar theory that one uses in the rings of invariance. So there are 2 groups of people who study this, but nobody seems to have studied it except for Markoff and Frobenius over Z. Because over Z it's very hard, but there are people who've studied over the real numbers, most notably Bill Goldman. I'll show you a picture now. So if you take the real points of the surface, you look at the mapping class group acting nonlinearly on this, and what he shows is that K is less than 0. So remember the equation? There you go. It's on the slide before. I'm a slow learner. This is kind of funny. If K is less than 0, then Goldman shows, or maybe I should show you the picture, and since I can have both of them up on the same time, it's even better. So here's K less than 0, k equal to 0. There's a point right there, S0, it's called S here, is the origin. That's one point, which is invariant under the action of gamma. You can check that by those Vieta moves. And then there are 4 components. This is called the Teichmuller space. Each one's a component of Teichmuller space. And gamma acts properly, discontinuously, non-linearly on each of these 4 surfaces when k is less than 0. Now, as I increase k, the equation's gone, sorry, but as I increase k, so k goes from 0 to 2, then the point there starts to grow, and there's a little blob here. And that blob is invariant under gamma, and what Goldman proves is that gamma acts, there's a natural volume form there, symplectic, this action symplectic, there's a natural invariant measure. He proves this action is ergodic. So this is the kind of thing that a dynamics person wants to understand. And 1 equals 4, k equals 4 is the famous Cayley cubic, because it's got exactly 4 conic singularity points there. Everything I say today about k equals 4 is false. So I will remove k equals 4 right now, because the action there is essentially in other coordinates linear. It linearizes, and that's why Cayley was so eager to find this cubic where he could make computations very easily. And his famous proof of 27 lines on a cubic uses exactly this Cayley cubic, that computation. At that point, he needs to show that some expression's not 0, and he can check it at that point, and then it's true. He only proved it for Zariski open set. Remarkably, when k is bigger, when after the connect there, then the surface now becomes one connected surface, and the group still acts ergodically until k equals 20. And at k equals 20, there's a non-wandering domain that appears. Okay, so that's the action over the reals, and it's a beautiful piece of work of Goldman in understanding it. And you can imagine that when you do reduction theory with a linear group, the first thing the reduction theory of Gauss is always over the reals. So this kind of picture is probably in the background of what we're going to do. Okay, I should say that the case k equals 0 is Markoff's case, and his very famous theorem is for Markoff triples, which is just a variation on that, is that, well, he's not interested in the orbit 0, 0, 0. There's another orbit, the point 333 in the notation I gave you, is an integer point on the Markoff cubic, x0k, and there's only one orbit. And that one orbit is a way of traversing all the solutions, and his interest in this was to relate that to Diophantine approximation. He showed that the best approximations to an irrational number, like the golden ratio, corresponds to the point 333. And then these Markoff moves move you up and down on the integer points. But his argument, and k equals 4 is very special, the argument that there are only finitely many orbits keeping away from k equals 4 is easy. It's an argument in infinity, and this divisor at infinity is extremely important. And this was generalized by Hurwitz, and later by Mordell, in these kind of equations, in saying there is some kind of reduction theory. And in particular, hk is finite for every k. So there's a class number here, is how often we hit each k by this Markoff cubic. And it's a special case of a general thing like this. So the first thing that you could do is you could ask, well, what are the congruence obstructions to solving the Markoff equation? So I'm now asking for a Hasse principle. For which case is there an integer solution? The point being that once there's an integer solution, I'll have a lot of solutions because the group, so as Gross, who's fast asleep here, okay, he's responding, so he's not quite comatose. He said that there are 3 guys here over 60. You'll have to wake us up all the time. And that's what I'm doing here. So as you said in the lecture, there's a difference between an elliptic curve and a curve of genus 1 because there's no point there on which you can start adding. And that's the same here. If we don't have any point on this, I can't start applying the group. So it may be the empty set. And I'm very interested in which case there's already 1 point. Once there's 1 point, then I get ambitious to understand that strong approximation may hold. So you look for congruence obstructions, and it's very easy that unless k is 3 mod 4 or 3 or 6 mod 9, there's no local obstruction. And so throughout, k will be assumed to be not one of those numbers. And I'm going to remove another little set. I'm going to avoid the set where one of the coordinates in the solution is either 0, 1, or 2, or -1 or -2. This removes a set of k's which I understand completely, because once I fix one of those coordinates, I know what the k's are it's a binary quadratic form. They should be handled separately. Zero density. So the number I'll call k generic, and what it was called in the first lecture I learned by terminology, apparently, that I just learned this morning, locally soluble. I just call it generic, that it's locally soluble everywhere. We're working out the integers. And I've removed these other guys. It's my definition of generic. And if you compute how many k's there are up to capital K, there are about 7/12, which you are left with, which are the generic k's. Those are the guys for which you might have an integer point. And the Hasse principle would be true if whenever you pass the local obstructions, you get an integer point. All right. Bourgain cubes. This is where he came up with this amazing composition law. It's on the cover of the poster, and I'm using it. And it turns out if you take a solution to this equation and you put it in a Bourgain cube, you get something very interesting. So I thought you might be amused by this. So in the end, you don't need this, but it gave us the definition of the completely accurate height to do reduction theory. The usual height that Markoff uses, well, take the biggest of x1, x2, x3 and try to reduce it. Or take the sum of x1, x plus x2 plus x3, they're all positive. But we don't have those conditions. We have this group gamma, and you'll see now a completely beautiful expression which maybe has some meaning to you. All right, so you take a Bourgain cube where you put 1 in the opposite sides, x1 in the opposite side, x2 in the opposite side, and x3. And then you take these 3 slices that Van Joule used in order to define the composition. So these are 2 by 2 matrices which come from the slicings. And then you form the determinant just like in the there's certain procedures here that Van Joule loves, so we're following it. So we form these 3 quadratic forms which come from the 3 pairs of slices. Because we're looking just x1, x2, x3, are these 3 forms, what I call self-reciprocal, the first and last coordinate. The A and the C in the binary form are the same. And then they have a common discriminant. And I should say, Ghosh was fiddling around with this, and he looked at this discriminant. And this discriminant is the most beautiful expression in the world. And you compute it, it's that function of x1, x2, x3. It's a sort of ultimate height function, as I'll convince you now. So it's a function. Stick to the generic. And now, in order to understand whether I'm doing some improvement, I want to understand this descent very accurately, where I start with some point. I use my group gamma to make it somehow lower height. So I'm going to use this delta, which we're going to stick to k. We don't have this theory if k is negative. It's more complicated there, not so clean. So if you apply a Vieta move, delta 1, delta 2, delta 3, and see which direction you're going, I removed the x2 and all the small values, so we're on this generic k. So the sign in which you'll move is this dictated by the prefactor there. And then it's a very easy argument to see that you have something like Gauss reduction. I'm going to give you a fundamental domain for this nonlinear action, which is in 1-1 correspondence with the number of orbits. All right, and the theorem is, and I call it Gauss reduced form because he found this rather beautifully. For k greater than equal to 5, you look at, I prefer to just point with my finger, is that okay? I should have a stick. This is silly little light. All right. You look at the real solutions with the elements ordered, and U1, U2, U3 in order, because you have the permutations, and bigger than or equal to 3, because I removed those small solutions. And satisfying the equation, U1 squared plus U2 squared, plus U1, U2, U3. They're all positives, and any finitely many solutions to that equals k. And then the theorem is every orbit of gamma on the Markoff surface is equivalent to a unique solution where you flip the sign. So in other words, if you each solution here, you make x1, x2, x3, where you flip the first guy to negative. That's this pocket in which it landed up with 1 coordinate negative. And that's 1 representative out of each orbit. Looks very much like Gauss's mod B, mod B less than or equal to C, A less than or equal to C. So interesting, it's a nonlinear action, but the fundamental domain is linear. The equation, of course, is linear. So, of course, once you have something like this, you can start to study this. And in particular, you can compute the class numbers galore. Because this now tells you exactly how many orbits there are for every k for this nonlinear cubic equation. Here's an example of a cubic surface. The K is equal to 3658. Class number 6. So there are points. I'll tell you a bit later how many points there are. There are many points here, but there you see the fundamental domain there, that little triangle in there. It's got 6 points inside there, and that's the class number of H of that number. Now, then you can compute easily, just like you would class numbers of binary forms. But here, of course, the class numbers are small. It's exactly like cubic forms, where the class numbers want to be small all the time, just because it's a cubic it's a degree 3 equation in 3 variables. That's how you count how often you're supposed to hit. So we are expecting to have the class number small. And the numerics computed so we were very interested in Hasse failures. So which K is there a Hasse failure? And the numerics show this is the percentage of Hasse failures up to K up to 2.5 times 10 to the 8. So we're going way out there. And the percentage of Hasse failures, starts at 10%, so that's 1/10 of them. And as you can see, once you go down, it's going down quite quickly. And it fits very, very accurately a curve which is saying that Hasse failures are rare. They occur at about K. The number of them seems to be infinitely many, and the number of them is about K to the 0.88. And only recently we actually know how to predict this number. Not exactly, it's very close to what we can predict by some probabilistic reasoning. So the story is that it seems numerically that Hasse is true for most Ks. There's an exceptional set, and now I can tell you what we can prove. So the first thing is we can compute the average value. That's always a volume computation, just like in all the counting that is the final step in Manjul's many, many theorems. Tentacles don't mean anything to me here. I don't know that I'm supposed to remove some guys, which if I were supposed to remove would make much happier. But there's no obvious thing to remove here, so there's an extra log K squared. And that's coming from the fact that we have this fundamental domain, and now we're just counting the number of integer points under a set which has got, it's like the divisor function, like hyperbola, and it produces an extra log squared in this case because it's 3 variables. Okay, that's the first theorem. The second theorem is that there are infinitely many Hasse failures. And I want to explain that a little bit. That's kind of took us a while to understand. So we have a Manin-Brouwer type obstruction here that is shown to hold for at least square root of K. So when I was saying it was K to the 0.8 or something, whatever the number of failures are, they're infinitely many, and it's at least K to the 1/2 of them fail. So there's no good reason that we know that they don't have points. They just fail to have points. But the K to the 1/2 of them, we have an obstruction, which is a global reciprocity obstruction, which removes those points. And the third theorem is a little, okay, I learned that when you have a theorem which you're still writing up, and when you're over 60, that means it could take 20 years, and Ghosh is not far behind me, so we're writing it up. He's writing it up, I should say. More. I'm sure the ideas are robust. So it's going to prove, unfortunately, not so far we don't see how to prove that almost all Ks satisfy Hasse, but a positive proportion do. So it's already better than we know for binary cubics. A positive proportion. So I told you, Cohen-Lenstra will tell you an exact proportion of how many guys you hit. We're saying that we hit a positive proportion. And the techniques here, comment 3, are based on techniques of Bourgain and Fuchs in the theory of thin groups, curvatures of integral Apollonian packings, which is kind of a mixture of the circle method and combinatorics. And it's extremely useful here to produce a positive density of Ks for which there is an integer point and Hasse is true. So that I would just refer you to that paper as one of the key ingredients there. The proof of the average is once you have a fundamental domain, it's kind of straightforward. That's not a problem. And the proof of this Manin-Brouwer obstruction, I'll just give you an example of a sequence. Here's an example of Hasse failures. If you take K equals 4 plus 2 nu squared, where nu has all its prime factors, all the prime factors of nu are either plus or 1 mod 8, and nu lies in this progression there. So this is basically a quadratic. This is the K to the 1/2 points, and we have other examples of this. Then there's a global obstruction, which I won't go into, but something that is close to what Cassels and also Mordell had found in some other equations. using global reciprocity shows that you can't solve the equation for these types. I want to emphasize one point here, is if you reduce mod p for an arbitrary large p k, it'll be, and p is congruent, suppose k is congruent to 4 mod p. Then when you make that reduction, you're looking at the Cayley cubic, and this obstruction is based on the Cayley cubic. The Cayley cubic is the only guy that's different to everybody else, and you can use it to make an obstruction. So the Cayley, that's why this number is 4 plus 2 times something. When you reduce mod certain p's, some interesting things happen. So to me, this is, as I'll explain, this is just the beginnings of a Hasse principle for these kind of equations, in which you have, for some reason, a group acting, and it's not the usual business. It's the group doesn't make sense over R. It's not like SL2Z, which you talk about SL2QP, SL2R. This is a group of symmetries. It's a discrete group, doesn't change. You change a field, it doesn't know. It is the mapping class group in any generality. I want to now discuss that. So part 2 is work with Bourgain and Gamburd, and here we're going to assume we have a point. So suppose I start off with a point, and it's not a point of finite order for this group. I will return to that. That's a fantastically interesting question connected to Paine-Lavey, which I'll explain in a minute. This is a very rich theory, and the more you look into it, the more you realize how it's at the center of many things. So I remove a special case, which I'll return to. And once you have a point, this group now takes this point, and we have something to hit it on, and we get many points. It's very easy to show the points are now Zariski dense in the surface xkc. So we now have a tremendous number of points. You might wonder, doesn't this violate conjectures of Voiter, which say that which generalize Ziegel's theorem, which says that if I have a plane cubic or degree, they only finitely many integer points. So there's nothing, we'd be out of business there. Here I've got an infinite, in fact, integer points. And the answer is, if you look at what Voiter's conjectures say exactly, you have to look at the divisor at infinity of this affine variety after you compactify it in projective space. And if that divisor infinity is at all complicated, this is like the plane minus 3 points versus the plane minus 1 or 2 points. If that divisor is complicated in the way it intersects and how many components it's got, then Voiter conjectures that you cannot have a Zariski dense set of integer points. So most cubics are not going to have many points, and this has to be special, and the divisor is a triangle in its very special position, and that's connected with the symmetry group gamma. Okay, so we have this group, and one is Zariski dense. And the big question that we're very interested in connection with Markoff numbers and all solutions of this type, about which very little is known, nothing basically, is if I reduce mod q, do I get all the solutions mod q? Could there be enough integer solutions here to have strong approximation? Now, there may be some q's which are small for which it fails. When I mean this question initially is q is large and maybe it's a product of large primes. So there's some number after which something will kick in. So, and what's the big difference between a linear and nonlinear action is the group gamma, or the mapping class group acting here. If I take the solution z mod qz, xk z mod qz, that's a finite set. And the group, I just reduce the action, it's now acting as a permutation group. Now, whenever you prove strong approximation classically, you'll end up in a general linear group or in an algebraic group, and you use the structure of these groups. Once you have a permutation group, there are many, many subgroups, many groups. And as q gets big, this has got q squared factorial elements, and you're trying to prove this action is big orbit. So this makes for a completely new set of problems which we can handle, as you'll see in a second. Anyway, so the question is, we have the mapping class group, and now it's acting on this finite group as permutations. What is the image? Could the image be very big? And of course, if the image is big, then we have strong approximation, because we have one point. So imagine there's one orbit. And I only have one integer point upstairs, because I am assuming I have one point. Then this group will take me to every other point mod q, and I have strong approximation. Something that a torus can never satisfy. So the linearity might help me here to be big, but it's got to be big in the permutation group. And theory, well, theorems that I'll show you in a minute show, is that in fact that's true to the extent we can prove it, that the orbit usually wants to be, as in the previous lecture, Dick was talking about the monodromy the computation of this group, which was for G large, was the symplectic group. It's usually as big as it can be unless you see some structure. So here the thing's acting with no structure. It should be big. And that's the philosophy, and that's what the theorem is. So I want to explain that there's no cubic surface over the integers for which we know strong approximation at all. You're allowed to make it any way you want. The only thing we understand is Torah. So this is the first candidate for which maybe we can prove, and we do prove, a good portion of the strong approximation. And I want to emphasize why that's hard from any standard analytic methods. When you do something with analytic number theory of the Hardy-Littlewood type, crude stuff, I see Browning there. It's powerful, but it usually requires many variables, and the number of times you want to hit somebody is usually large. So if you ask, can you use the circle method to prove every positive integer is a sum of 4 squares? The answer is that's already tricky. 5 squares is easy because you're hitting each number a tremendous number of times. 4 squares, you're still hitting it about n times. 3 squares is really hard, and the circle method falls short. Then you have to use other methods. 2 squares, you can't do with analysis. You have to. That's Fermat. So that's algebra and factorization. So we understand homogeneous form affine varieties with quadrics, and we're trying to understand the cubics. And because there's a cubic form in 3 variables, it turns out the number of solutions in that picture that you had before, the number of solutions in a big ball, is very sparse. So it is a lot like a torus. The number of guys whose height in a big ball of radius t is only log t squared. For the case of the Markoff equation itself, this was proved by Zargier many years ago. He was counting the number of Markoff numbers in t. And he got a constant here. And I understand it's a place he made a calculational error. I'm looking at him. It's not your fault. I don't know if that's true. That's according to this fellow Bumby who reviewed the paper. Anyway, Zargier's method was quite elementary and very clear. But it turns out you can study all these equations and higher character varieties with the recent work of Mirzakhani. So these solutions are very sparse, and so it's kind of remarkable that if you reduce mod q, you might be getting all the solutions mod q. But the reason that might be true is because we have this big group acting, and we need to understand its orbits. It's the group that's going to save us. All right, so before we start to try and understand what strong approximation might read here, you have to first ask yourself the question, what are the finite orbits? So now we have to do dynamics, and we start to get nervous. I mean, we look at the complex points, and we say, what are the orbits of gamma? Well, I'm going to look mod p. I look at the field with p elements, and suppose there's some finite orbit whose coordinates are q bar in q bar. The finite orbit whose entries are in some finite extension of q. Then I will see this mod p. Mod p knows about all the algebraic q bar by Chebotarev. There will be a set of p's for which I'll be trapped in this finite orbit mod p if those coordinates were already in fp. So I can't even formulate what strong approximation is until I've understood a very basic question. And the basic question are not what is the ergodic theory of this on the complex numbers, which nobody knows. I told you about the work of Goldman. That's for the real numbers. So for the complex numbers, it's completely mysterious what the action of the mapping class group on these affine complex surfaces is. But I just need to know what the finite orbits are, because they're my enemy. And it turns out, and this is a theorem that we prove using Lang's GM, and I want to tell you a quite amazing story about this. It turns out there are only finitely many finite orbits, and you can determine them explicitly. So before we start, we can find these finitely many finite orbits. Those are the enemy. They don't depend on p. And then whether they're there or not, when I look mod p, if the coordinates, this is over q bar, if those coordinates lie there, I remove those, and then I can state the main conjecture and the main theorem is that the complement is one big fat orbit. That's what's happening here. But I have to first understand these finitely many orbits. And when we put this on the archive, I kept on thinking, why does nobody know this theorem? And I started looking at the literature and finally found that there are 2 mathematical physicists who proved this theorem before us in this case. And they are the famous Dubrovin and Machaka. And they were studying the following question, which is popular in mathematical physics. This is a solution, just like Schwarz's list of the list of all F21s which are algebraic functions of their z. So you're looking at a second-order ordinary differential equation, Gauss's hypergeometric function, f, alpha, beta, gamma, double colon, z. The z is the variable, the alpha, beta are parameters. For which alpha and beta is that an algebraic function of z? And Schwartz gave a very beautiful solution using monodromy. This is why Riemann invented monodromy. And of course, the equivalence there is known to everybody. That function is a function which is algebraic in z if and only if the monodromy is finite, a finite group, because then you only have finitely many sheets. So Payne-Lavey wrote a system of 6 families of ordinary nonlinear differential equations. Here's what they are with 4 parameters, which have the property that the solutions are meromorphic in the plane, except for essential singularities at 0, 1, and infinity. So again, we have the monodromy going around these same cycles. But the monodromy group now is a nonlinear action. It's a nonlinear equation, so you don't start with a vector space and come back around and then back into the vector space. You first have to parameterize solutions. So if you parameterize them by the value of the function at a point and the first derivative, those are terrible coordinates, but those are, of course, so it's a surface. So there's something called Schlesinger coordinates, in which the monodromy action can be computed as you go around this, and lo and behold, the surface for a given equation is a Markoff surface with some k, and the nonlinear monodromy action is gamma, is the mapping class group acting. This is just incredible. And so what does he need to know to complete the list of all Payne-Lavey 6s? Payne-Lavey 1 to 5 are trivial because they are abelian monodromies. That was well known even by Payne-Lavey, the first ones, I think. So Payne-Lavey 6 was mysterious. You need to know the finite orbits over finite orbits over C of gamma action on affine 3 space. The exact thing I also want to. So it turns out they solved it. Then I'm looking at this paper. How on earth does he do it without using Lang's GM? I know what my trump card is. and I know exactly when I use it. Well, he found an old theorem of Kronecker about roots of unity, which is the standard starting point for many proofs of Lang GM for a torus. And that was enough for him and Mozzocco to do this case. The general case he couldn't do, but it was done by those other authors. All right, so we remove these finite number of orbits, which we a priori determine, and in fact the entire list. So by the way, so Mozzocco and Dubrovin give you the analog of Schwartz's list for Payne-Lavey 6. It's a finite list of guys which are algebraic functions. Beautiful, beautiful thing. But it's a Darwinian theorem. All right, as our main conjecture, and then I can tell you what we prove about this. So if you remove the finite, I think at this point it's kind of obvious, you remove those finitely many finite orbits that you determine before you start, and I call the complement xk star, and the claim is that if P is sufficiently large, for P, our proofs only start to kick in when P is large. I don't know what's happening for P small, except for the Markoff case. When P is large, we're going to be one fat orbit, we have strong approximation. That's a conjecture. And if it's 0, it's a Markoff case, so you can see that the only guy you remove is 0, 0, 0, and we've checked numerically, so the conjecture is everything is always onto, that monodromy is this group acts on these bigger and bigger, this permutation group acts transitively on the points, on all solutions. Okay, so we have a theorem. The first theorem is general, it's a starting point for the proof. Now our proofs of this, the usual techniques that I'm familiar with don't seem to apply, so we are just making up methods as we go along, using combinatorics, Riemann hypothesis for curves and beyond, as I'll explain in a minute. So the first theorem is there's always a big orbit, I call it OP, contained in, remember we're expecting it to be one orbit. So the first is there's a giant orbit, so that there's a set which is gamma connected. In other words, you can go with your transitive. It's the actual closure, the orbit is bigger than OP, but if I take the closure of that, it might be the whole thing. The complement is at most P to the epsilon for any epsilon. I call this a giant orbit. Epsilon's positive. The number of solutions is about P squared. That's elementary. So we have this big giant orbit that our techniques provide. And moreover, and this is very important because this connects, at some point I have to make a lift to characteristic 0, and that's where I face Dubrovin's list. Has to come somewhere in the proof, because where am I using that? The theorem is that except for those finitely many that you determine a priori, every orbit has at least log p to the 1/3 point. So no orbit is tiny, it's growing with p, and then there's one big giant component. And then the second part of the theorem is we want to connect everybody to the giant component and say there's one orbit. And that turns out to be quite hard, and in fact that's the only reason that we don't have a proof for all p, is that we have an enemy. If p minus 1 or p squared minus 1, if p minus 1 has a tremendous number of prime factors, so if it's equal to m factorial, now I don't know if there are infinitely many primes of the form p minus 1 is m factorial, but I have to entertain it. If it's got a lot of prime factors, the proof is very much got combinatorics in it, and the divisors of p minus 1, which are in a row, very close to each other in a dyadic interval, because we're doing some exclusion, if there's a whole sequence of such divisors, we run into trouble. So if p squared minus 1 is very, very smooth, we run into trouble, and the proof doesn't work. But the number of primes for which that's true is tiny. In fact, presumably, there aren't any primes which are exceptions to our argument. But all we can prove at this point is that the set of exceptional primes for the main conjecture is at most t to the epsilon when looking at primes up to t. So it's not zero density, it's tiny. We could probably improve that to log. Should be empty, should be finite. No, it shouldn't be empty, it should be finite. That's already enough to execute the various serving arguments that we entered. And once we're this far, you could ask, well, this is just saying that permutation groups acting transitively. You could ask, what is the group? It's after all a permutation group. And it turns out, so far only if p is congruent to 1 mod 4, there's something special in that case, that Genmeier and Dorum Puder, just a few months ago, were able to prove that when the group is transitive, then it's either the full symmetric group or the alternating group on those letters. So the image is as big as it can be. That's what should be happening, and it's actually a theorem here for the p's for which everything's working. All right, I have 2 minutes. Let me say a word about the proof and just get back to Lang's GM, and I want to explain one point which to me is the most juicy point of this, is one does use transformations. So I'm very scared to iterate nonlinear maps personally. So we're going to live by just making many different linear maps by playing games. And these are called Dane twists. So the Dane twists, remember at the beginning we had these 3 Vieta involutions. Now suppose I fix the first coordinate. The Vieta involution was I fixed 2 coordinates and just flip the third. Fix the first coordinate and take the composition of the one involution with the other. This will now be a linear transformation in x2 and x3. The first coordinate's fixed. And it will be, its powers as it acts on that plane will be given by linear transformation. So what I'm going to be doing here is taking this Markoff surface and I'm intersecting it with a plane. One of the coordinates is constant. And then there are these rotations, which are called Dane twists, which are preserving this conic section. And so I have this conic section, and if the order of this rotation were full, as big as it could possibly be, and this rotation is, of course, a 2x2 matrix, so it's in SL2FP. This is where the divisors of p squared minus 1 eventually are an enemy. But if the order is very big, then the rotation is actually going to fill out the whole quadric, a whole conic section. And then if I take another section, it'll fill out that whole conic section. Then I can try to connect all these conic sections to each other, because they're going to meet each other, and then maybe get everything's in my orbit. And that's exactly how you proceed. But your big enemy is, well, maybe you start with, so the giant orbit is made this way because you just choose your element to be large order. And many of them have large order, and that's this giant orbit. But now when I start with something that's very small, if it's really tiny, it's sitting in that bad set to begin with. And you make that effective. And once it's growing a little bit, I want to show that it's connected to somebody which has got an order which is bigger than it started off with. And then iteratively, eventually land up in the big set. And eventually you'll end up counting the number of solutions to unlikely intersections. And that's a beautiful problem, and I just want to end with that. So you'll end up having to count the number of solutions to, over a finite field P, Fp, or Fp star, of this equation. It's a plane curve, C plus B over C, B is not 1, equals eta plus 1 over eta, where C is supposed to be in a finite subgroup H1, and eta is in a subgroup of finite subgroup. Let's say they're both in FP star. You might have to go to a quadratic extension because these are the eigenvalues of the 2x2 matrices. And you want to give an upper bound number of solutions of that where H1 and H2 are the order of these groups. And let's say H1 is not almost the whole group. And you want to give, as I said, an upper bound to this. And the trivial upper bound is clearly H2. Once I choose C, then eta is two choices. But I want an upper bound which gives a power on H1 so as to do this iteration. And this is the order of my starting guy, and I want to connect it to a beta guy. And the guy that I start off with, if its order is bigger than p to the half, then you give a bound for the number of solutions to this equation handsomely by using the Riemann hypothesis for curves of a finite field, because the genus of the curve that intervenes is less than root p. The Riemann hypothesis for curves gives you the number of points on a curve is p plus 1 plus something which is at most g times root p. If g is bigger than root p, that statement is completely useless. So it turns out that if the order's big, you win. You can connect up and you win by using they. But if the order's small, the Riemann hypothesis gives you nothing. So we have to go back into the proof of the Riemann hypothesis by Stepanov using auxiliary polynomials. He gave an elementary proof of the Riemann hypothesis for curves, which has much more information in it. And it allows you here to get a bound which is always non-trivial, no matter how small h is. And that's something that's really critical here, is the use of that. Quite incredibly, Bourgain found a different proof, and this really annoyed me. Where did this come from? He found a combinatorial proof just for this problem, a Semeretti-Trotter theorem, projective Semeretti-Trotter theorem that he proved 3 years ago that nobody noticed, that also allows for the same, not with constants and somewhat weaker, but it's a combinatorial proof, so you can then, it's about counting points with certain incidences between PGL2 FP actions. So we give two proofs in our paper, and that's kind of an unusual ingredient. All right, I won't talk about Lang's geom. I'm running out of time. I just want to say that this is just the first of many, many such examples. And in fact, a student at Princeton, I call him Peter Wang. I think his last name is Wang. His first name, I like Peter. So Peter Wang has really made some big fundamental inroads to deduction theory and the complex geometry of the character variety that's connected with understanding integer points, log Calabi-Yau, he's already made these breakthroughs, and I believe that this is just the beginnings of the theory that maybe one day Manjul will come over to and change in a way that Dick Gross ended his lecture for years to come. Thank you. Yeah. Yeah. They're very small. They get up to, so in the more general, when you want to do this Pain-Lavey properly, you need not just this particular character variety, but one more, the four-hole sphere, which is a bit more complicated. And all of them correspond to, so there's Bolach, a student of Hitchin, who was putting elements. So the solution of these problems came out of two directions. One, people writing down by clever constructions using algebraic geometry of Pain-Laveys which were algebraic. And then this, which then said this is the entire list. And then most of those correspond to the Platonic solids. So the fields of definition of linear rotations in Platonic solids. But there are 2 or 3 exceptions which are in bigger fields. I can't remember what they feel, but it's definitely bigger, indicating that there's probably no other proof, or we don't know any other proof other than Lang's GM, which I didn't explain. So when they do it, they don't know Lang's GM, but they reproved some part of it. Lang's GM, so you can see this where Lang's GM would come immediately, is if I have these Dane twists, suppose my group, I'm looking for a finite orbit. So each of these rotations now has to be finite order, but I don't know the order. So the Dane twist has finite order. Its eigenvalue, which I'm calling now lambda 1, so lambda 1, all of the eigenvalues of these 3 rotations must be roots of unity. So I get a nonlinear equation, polynomial or unpolynomial equation, in roots of unity. That's exactly Lang's GM. That is, it looks like a nonlinear problem, but you can replace this variety cut out by this equation by tori or translates of tori, such that all the solutions already lie in these. In this case, they only finitely many. And they are those, and that's an upper bound. That then gives you a set which your finite orbit might sit inside. Then you go back and check whether gamma preserves that, and that happens very rarely. So it's a list of about, I think the Paine-Lavées, which are algebraic, the list is something like 50 of them. It's like Schwarz's list, actually. It's an amazing thing. Yeah.
You mentioned in theorem 3 integral Apollonian packing. How
they connect? How do they come here? Yeah. So I'm trying to prove that the set of k's which are positive density, a set of k's for which Hasse is true. So this is, remember what the equation is. It's x squared plus y, x1 squared plus x2 squared plus x3 squared minus x1, x2, x3 equals k. To produce k's. So if I want to produce many k's, one obvious way to do it is fix x1 equals 1, and I have a binary quadratic form. The number of k's that produces is zero density. It's a theorem that many of Manjul's students have come, and they love. Melanie Wood, for example. It's a number of ideals, the number of distinct numbers which are norms of ideals in a number field, is x of a square root log x. You can prove this with a sieve, or you can prove this, the theorem really goes back to Landau. You can use the zeta function of the number field. But that's zero density. And now what happens is I want to take many x's, so that produces for me already many guys for which a Hasse principle is true. Now I take another x, and I hope that produces some new guys, and I increase x, and then I have to make sure that I'm producing enough to eventually get positive density. Now, of course, if x gets too large, I must be producing the same numbers again. There's not enough room. So the question is, can you go just up to some distance to get positive density and use the structure of intersections of a binary form equals a binary form, a non-upper bound? And for that, you use Klostermann's method for a quadratic form solving a number, and Klostermann's methods are what they use. So they use this to prove a positive. There was a conjecture about Apollonian packings, whether the curvatures in Apollonian packing are positive density. And they proved that. That's the theorem of Bourgain and Fuchs. So that's the connection. The technique's the same. There's no connection that I know otherwise. The Apollonian is a linear action, but the group's infinite index in a natural arithmetic group. Here the action's just really nonlinear and much more interesting in a way.
Any other questions? Thank the speaker.